Now we'll start the details of this elementary proof of prime number theorem. We'll begin with introducing two auxiliary functions. First, recall the theorem for 20. Pi of x is similar to theta of x divided by log of x, similar to psi of x divided by log of x. Now to prove theorem 6, namely the prime number theorem, it suffices to prove the following theorem for 34. That psi of x is similar to x. And to this end, we put psi of x equal to x plus r of x. Then it follows that psi of x similar to x is equivalent to saying that r of x is a little o of x as x goes to infinity. And next, we're going to use Selberg's asymptotic formula. The first thing we do with the Selberg's asymptotic formula is that we are going to replace psi of x in that formula with r of x. Now recall theorem for 24, which is about the summation of lambda of n divided by n for n less than or equal to x equal to log of x plus b equal to 1. We prove this in the section an important sum. Recall this and theorem for 33, Selberg's asymptotic formula. This is theorem for 30 in Hardt's book, but I believe that is a typo. Specifically, we recall the first formula there. There are two formulas for Selberg's asymptotic formula. Here we are using the first one. And now we replace psi of x with x plus r of x. Now, using theorem for 24, we can make a big simplification to this Selberg's asymptotic formula with psi of x replaced by r. First, this term can be rewritten as and by theorem for 24, we can see this term is equal to x times log of x plus big O of x. Now, you see a beautiful cancellation of 2x times log of x from both sides. And this big O of x will merge with this big O of x. Therefore, we get a rather simplified Selberg's asymptotic formula from here. And there's a label to this in Hardt's book. This is the equation 22.15.1. From now, we'll use this simplified Selberg's asymptotic formula to prove a couple of formulas consecutively. The first formula we're going to prove is the following. We show that the absolute value of r of x times log of x squared is less than or equal to, and the coefficient here is, at this point, please recall that the summation of an's is precisely the left-hand side of the second Selberg's asymptotic formula. So this is the first formula we're going to prove. The second formula we're going to prove is something that you replace this part on the right-hand side by an integral. And there will be more formulas following these two. But we will start by proving 22.15.2. We start with this simplified Selberg's asymptotic formula. And we shall replace this x by x over m. And now we take the following subtraction. We multiply log of x to the left-hand side of this equation minus the summation for m less than or equal to x of lambda of m times the left-hand side of this equation. On one hand, this difference will become, which simplifies it to, now here, again we are using theorem 424. By theorem 424, this guy becomes, now you pull this x to the front. And this gives you a perfect shape of applying theorem 424. And combining this will give us still big O of x log of x. And on the other hand, we can also simplify this directly. So how is this simplified? We're just going to distribute these brackets. Note that this sum is indexed by n, but now we'll change this n to m for convenience, which cancels with this guy up to a factor of log of m in each individual summand. Now combining this guy with this, we conclude this new identity. And now we do the following. We first change the variable here from m back to n, and we'll change the sum here into a graded sum or stratified sum. So we first change the variable from m to n here, and we will change the sum here in the following way. For each n less than or equal to x, we look at all hk equal to n, and we take the sum of all of lambda of k lambda of h r of x divided by n. So this guy is the same as above, equal to big O of x times log of x. And now we move these two parts to the right hand side, and we use the triangle inequality. We get the absolute value of r of x times log of x squared bounded by this sum with x value on each segment plus this sum plus the last term is big O of x times log of x. And now let's merge these two together. From here, we realize that its coefficient in front of the absolute value of r of x divided by n is precisely a sub n. By definition, this is a sub n. And with this, we have proved the equation 22.15.2.